Hey there. Let's talk about number system. At its core, programming is about storing and manipulating data. And all the data, be it text, image, audio, or video, is stored as numbers inside the computer. This makes it a good enough reason for us to understand the number system. Also, understanding number system will better prepare you for understanding the concepts that we are going to discuss in future. For example, the shift operator. With this said and done, let's discuss what a number system is. In mathematics, a number system is considered to be the notation of numbers using digits or symbols. In total, there are four different types of number system. The decimal number system, the binary number system, the hexadecimal number system, and the octal number system. Let us talk about each of them one by one. The decimal number system is also known as the base 10 number system. And this is the number system that we use for everyday tasks like counting people or keeping track of score, etc. The reason this is called base 10 number system is because we have got 10 digits at our disposal to represent any number in decimal number system. And those digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Similarly, binary number system is called base 2 number system, and this is because we have got only two digits, that is 0 and 1. Likewise, octal number system is called base 8 number system because we have got 8 digits starting from 0 going all the way up to 7. For the same reason, hexadecimal number system is called base 16 number system because it has got 10 digits starting from 0 going all the way up to 9, and the remaining 6 are alphabets starting from A going up to F, making it 16 in total. With this discussed, let us talk about how can we represent a number in any of these number systems. For example, if we were to represent 72 in decimal, we will write 72. That is it, right? If we were to represent 72 in binary, it will be 1001 000. Now, if you're wondering, how did I get this from this? We are going to discuss about this, but that will be a discussion in the next video. For this video, we will focus just on the number system and a few other concepts related to number system. The next video will be solely dedicated to converting one number system into another. And the reason I'm not discussing conversion of one number system to another in this video is because it will make the video very long, because there will be a total of 12 different combinations considering we have got four number system and each number system can be converted into the other three. Continuing, if we were to represent 72 in octal, what can we write? We will say 110. And in hexadecimal, it will be 48. Now, a question must be arising, that is, how do we know if this is written in binary or decimal? Similarly, how do we know if this is 48 in hexadecimal or decimal? Because as you can see, the value that this represents changes depending on which number system it is in. If it is in hexadecimal, it represents 72. If it is in decimal, it represents 48. So for that, what we do is we use a subscript. The subscript is 2 for binary. We also call it as base 2. It will be 8 for octal and 16 for hexadecimal. For decimal as well, we can put 10, but it is not required. If a number does not have a base, it is assumed that the number is represented in decimal format. For all others, we need to put base so that we don't confuse ourselves and others. Next, let's talk about position of a digit in the number, the positional value, the LSD or the least significant bit, and the MSD or the most significant bit. Let us start that discussion with decimal because this is something we are all familiar with. So if we were to represent 72 in decimal, this is how we write, correct? And we know that this is the ones place and this is the tens place. So if we want to find the position of 7 in 72, what we do is we go for 7 multiplied with 10. For 2, what are we going to do is 2 multiplied with 1. If this number was, let's say, 8972 instead of just 72, the 9 would have been in the hundreds place and 8 would have been in the thousands place, right? And if we were to find the value of 9, we would have done this 9 multiplied with 100. So if you see, whatever is at ones place is multiplied with 1, whatever is at tens place is multiplied with 10, whatever is at hundreds place is multiplied with 100, and so on. So can we say that this 1 is 10 to the power 0? and this 10 is 10 to the power 1, and the 100 is 10 square, and the 1000 is 10 cube. So what can we observe here? We start from the rightmost digit, and the rightmost digit gets the power 0. The digit next to this will get power 1, then 2 and 3 and so on. So we start all the way from the very right, put 0, then 1, then 2 and then 3. This 0 and 1 and 2 and 3 is called position of that digit in that number. Talking about 8, 9, 7, 2, the position of 2 is 0, of 7 is 1, of 9 is 2, of 8 is 3. And that is why what we do is, if we were to find the value of 2 in 8972, we do this. We use a digit and then multiply it with 10 raised something. And this something is actually the position of that digit in that number. So if we were to generalize this, what would we do? If we have a number in the format, say ABCD, and this is represented in decimal, and if we were to find the value of B in ABCD, we will do this. We will use that digit, multiply it with 10 raised its position, which is, let's say, P in this case. And this is applicable to decimal. The reason we are going for 10 power something is because this is decimal whose base is 10. Similarly, if we were to do this in binary, for example, we had say A, B, C, D in binary. And if we were to find the positional value of A, we would have gone for A into 2 power P. And over here, the value of P will be 3. This is how we can do it for binary. For octal and hexadecimal, it will follow a similar approach. If we have, let's say, ABCD in octal or ABCD in hexadecimal, and if we were to find the position of A in ABCD, which is represented in octal, we will go for A multiplied with 8 power position. Similarly, for hexadecimal, we'll go for A multiplied with 16 power position. So this is all about the position of a digit in a number and its positional value. If we have a number such that one of the digit repeats, and if we were to find the position of a digit, it depends on us as to which position we want to go for. For example, if in 2, 1, 1, 2, 3, 4, I want to find the positional value of 2, we will get two different answers. We will get 200 for this, and we will get 2 lakh for this, assuming this is in decimal number system. Now, all of this was related to whole number. But what if we have got a real number? For example, what if we had, say, 891.378? How will we find the position and the positional value of, for example, 7? For that, the process will be similar. We will start from the rightmost digit in the whole number part. If we consider this entire number as a real number, we will have a whole number part and we will have a fractional part. The fractional part will be the one after the decimal. For whole number, the process will be same. This will be at position 0, this will be at 1, and this will be at 2. And if you have noticed already, what we are doing is we are starting from 0. To get the next one, we are adding 1 to it, and to the next, we are adding 1 to this, which means we start from the rightmost digit, we go towards the left, and for each position, we go for a plus 1. Following the same logic, what will be the position of 3 over here? If towards the right it is plus 1, towards the left it would be minus 1. So if 1 is at position 0, 3 will be at position minus 1, 7 will be at minus 2, and 8 will be at minus 3. And assuming that this is in decimal number system, if we were to find the position of, let's say, 7, what can we do is we can go for 7, which is the digit, multiplied with 10 raised to the power something. And as we have discussed, that something will be the position of that digit in the number, which in our case is minus 2. So solving this, we will get 7 by 100, and this will be 0.07. This is how we can find the position of the digit in a real number. Following the same logic, let's say we have got a binary number. For example, 011.010. Or we have got an octal number, for example, 357.12. Or we have got a hexadecimal number, for example, AB.3F. How can we find the positional value of, let's say, this one in this binary number, and let's say this 2 in this octal number, and for example, this F in the hexadecimal number? Pause the video for a moment, try solving it yourself, and then follow along to check if your answer matches mine. So to find the positional value of 1 in this binary number, we will first of all have to find its position, which we know is -2 because this is 0, this will be -1. The one that we are interested in is at -2. What are we going to do next? We're going to say 1 multiplied with 2 power -2. Solving this, we will get 1 by 2 square, which is 1 by 4, which is 0.25. This, by the way, is in decimal. So the position of this 1 in this binary number is 0.25. Next, solving for the 2 in 357.12, which is represented in octal number system, we will have the position as -2. So we will say 2 multiplied with 8 power -2, and this will become 2 by 64, which is 1 by 32. And if you want to solve for 1 by 32, you can do this. We can start with 1 by 2. If you divide this by 2, you'll get 1 by 4. Dividing further by 2, you'll get 1 by 8, then 1 by 16, and lastly 1 by 32. So what you need to do now is go for 1 by 2, which is 0.5. Then go for 0.5 by 2, which is 0.25. Then go for 0.25 by 2. This will give you 0.125. 0.125 by 2 will give you 0.0625, and 0.0625 by 2 is going to give you 0.03125. So 1 by 32 is 0.03125. Continuing, let's find out the value of f in ab.3f, which is represented in hexadecimal number system. So the position over here is -2. We'll say f multiplied with 16 power -2. Now f in hexadecimal is equal to 15. To understand this better, we know that we've got digits from 0 all the way up to 9, and then alphabets from A to F. Now, if this ends at 9, alphabet A will represent 10, B will represent 11, C will represent 12, D will represent 13, E 14, and F 15. So that is how we know F is 15. So we'll say 15 multiplied with 1 by 16 square. And this will be 15 by 16 square is 256. Now we can find out the value of 15 by 256 also, but I'll leave that on to you. So this is how we can find the position and the positional value of a real number represented in any number system. Now with this clear, let's circle back to our example of decimal. Let's say the example was 891.589. And over here, if I ask you which of the digit holds the least value, how will you find that out? Well, one way is to find out the value that each of the digit holds and then compare which of them is the least. So let's quickly do that. For 1, it will be 1 itself. For 9, it is 90. For 8, it is 800. For 5, it will be 0.5. For 8, it will be 0.08. And for 9, it will be 0.009. Out of all of this, 800 is the highest and 0.009 is the lowest. If you take another example, or if you take any example for that matter, if you have got a number in this format, let's say abc.def, and I don't mean that there's only 3 digits in the whole number part and only 3 digits in the fractional number part. The whole number part can have any number of digits, and so do the fractional number part. But what I'm trying to say is, if you have got a real number or a whole number, the leftmost digit will hold the highest value every single time, and the rightmost digit will hold the lowest value. And the reasoning is pretty clear. As we go towards the left, we keep on increasing the power of 10. For example, over here, the power of 10 will be 2. Here it is 1, here it is 0. And to the extreme right, in this case, it will be 10 power minus 3. So this makes it a very small number compared to this. And the reason I'm talking about the highest value and the lowest value is because this translates to LSD and MSD. The digit which holds the lowest value is called LSD, or the least significant digit. And the digit which holds the highest value is called the MSD, or the most significant digit. So this is what the positional value, the least significant digit, and the most significant digit is in each of the number system. Although we have discussed only about decimal, it will apply to all the number system, be it binary, octal, or hexadecimal. My suggestion would be to take random examples and try it out for yourself. Next, let's talk about addition. Let's start with something that we already know, which is the addition of two numbers represented in decimal number system. Let's say we take 751.39 and we add this with 28.905. To make addition easier, we'll put a 0 over here and we will continue. The answer would be 5, 9, 2, 1 carried over, 0, 1, 8, 7. So this is going to be 780.295. Similarly, we can add numbers represented in binary number system. Let's see how. So if we have a number in binary number system, the numbers will have either 0 or 1. And if we go for addition, no matter how many numbers we add, we always go in groups of 2. So for example, if we have A, B, C, D, and E to add, we will add A and B, then add the result of A and B with C, then with D, and then with E. So every time addition will be done in groups of 2. Now taking that and this fact into consideration, that a binary number will have either 0 or 1 in the digit, we can come across a few cases. Let's talk about those cases one by one. Case 1 would be 0 plus 0. Case 2 would be 0 plus 1. Then the third one would be 1 plus 0. Then 1 plus 1. And then lastly, we can also come across 1 plus 1 plus 1. So 0 and 0 added together will be 0. 0 and 1 will be 1. 1 and 0 will be 1. 1 and 1 added together will be 0 with a carry of 1. And 1, 1, 1 added together will be 1 with a carry of 1. So keeping this in mind, let's take two numbers represented in binary number system and add them together. So let's take 1, 1 dot 0, 1, 0, 1, and let's add this with 101 dot 1, 1, 0, 0. So the first one is 1 and 0. We know 1 plus 0 is 1. So we will write 1 over here. The next one is 0 and 0. We know it is equal to 0. We'll write 0 over here. The next one is 1 and 1. And we know that it is 0 with a carry of 1. So we'll write 0 here, carry over 1 here. Then this becomes 0 and 1, which is 1. And 1 and 1 is this case, which we know is 0 with a carry of 1. And now we have got the last case here, which is 1, 1, and 1. And we know that this will be 1 with a carry of 1. This brought us to case 4, where we have 1 and 1, which will become 0 with a carry of 1. And then again, we have case 4, which is 1 and 1. So this will become 0 with a carry of 1. Now, as we don't have anything over here, we can put a 0 and this will become 1 plus 0, which is 1. So our final result is 1001 dot 0001. This is how we can perform binary addition. Next up, let's talk about string representation. There are a few different formats in which string is represented in a computer. For example, ASCII and Unicode. We will focus our attention to ASCII because you will need this knowledge to write code further down the line. Unicode is used by computers because it can represent any characters that exist universally. It could be in English, it could be in Hindi, or any language for that matter. And that is why computers use Unicode. For solving either a real life problem or the one related to DSA, ASCII will come in handy. So let's talk about ASCII. Now, if you're not familiar with ASCII, let me tell you that ASCII stands for American Standard Code for Information Interchange. This is widely used for encoding alphabets. So both uppercase A to Z and lowercase a to Z, digits, which means 0 to 9, and a few characters, for example, dot or close parenthesis, etc. Now in ASCII, uppercase A is represented as 65. Uppercase B is 66, and so on all the way up to uppercase Z, which is 90. For lowercase a, it is 97, lowercase b, it is 98, and this goes all the way up to lowercase z, which is 112. For digits, 0 is represented as 48, 1 as 49, and 2 as 50, and it goes all the way up to 9, which is represented by 57. Similarly, dot is 46, the closing parenthesis is 41, and there are a few other characters with their own values. Now, what you would probably need the most is this: uppercase A to Z and lowercase a to Z, and digits from 0 to 9. So this brings us to the end of this video. Summarizing, we talked about the four number system: the decimal number system, the binary number system, the octal number system, and the hexadecimal number system. Then we talked about the position and the positional value of a digit in a number represented in any number system, the LSD and the MSD as well, which is the least significant digit and the most significant digit. Then we also talked about binary addition. Then we continued with string representation and focused our attention to ASCII. In the next video, we will talk about how can we convert a number represented in one number system to another number system. I hope I've been able to teach you something new and useful. If you have any suggestions, feedback, or query, feel free to put them in the comments. Thank you so much for watching, and I'll see you in the next one.